So what's happening here is the function, the Newton-Raphson, will take you to the top of the quadratic. But that might be, because your function is not quadratic, actually at a lower point on your likelihood function. Okay? So you've moved from this point on the likelihood function to a lower point, worse likelihood value. What you do then is, or a standard approach, is to, instead of taking a step of 1, having that scalar of 1, which will move you here, and you kind of lose ground by moving there, is instead go a half of the distance. Whenever this happens, you know you've gone beyond the max. You've gone down, because you're going on the upside. You're going in the direction of the slope. And if you end up lower, that's because you've gone past the maximum. So in that case, instead of going scalar of 1, you go scalar of a half. And try what'll happen there. And look, in this case, it brings you pretty close to the max, right there.
But your gradient has changed sign, so if you still took the large step, wouldn't the reverse step? Well, you would go back to the same step.
Well, if the curvature were exactly the same here, but that's unlikely. It is true, you could go with just this Newton-Raphson without changing the scalar and go here, and then eventually it will reach the maximum. It'll just take more steps. But this is a matter of, if you know you're getting worse, why you've passed the maximum, why not try something different? It's very easy just to take the same step but half as far. That's a very simple computer exercise. You don't have to calculate the Hessian again, which is an expensive operation from a computer's perspective. And so the idea here is you first start with a scalar of 1. If that raises the likelihood, great. If it lowers the likelihood, you then try a half. If a half lowers the likelihood, you try a quarter. And you continue halving it until you've finally got a rise. Now, for reasons that we'll see in a second, you might not ever get a rise. Okay, and that's a failure of the Newton-Raphson procedure, and for a reason we'll say in a second. But in any case, you know that if your problem here is that you're going past the maximum, you can always halve the distance. Similarly, and this is the procedure that's put into all the Newton-Raphson procedures that I know that are in computer code. They changed this lambda, the scaling factor, appropriately for that. You can do the opposite, however, and this is not in any of the codes except the one that I wrote that you'll be using this coming week. Suppose you have gone to the top of the quadratic. So this is the quadratic. This is the actual. And you've got an increase in your function. So you went to the top of the quadratic and then go to your function, you've got an increase. Well, that shows maybe you could do even better by going further. So the idea there is, if you got an increase the first time around, double it, see if you still have an increase. If you got an increase when it's doubled, keep that. Or in fact, if you got an increase when it's doubled, double that and go 4 times. Just see how far you can go and keep getting an increase. Because every one of these steps, as long as all you're changing is the scalar, is extremely fast from the computer's point of view. Every time you stop and recalculate your Hessian, it's very slow. So as long as you're finding an increase, keep going. If you've gone to 4, then try 8. If 8 is below 4, go back to 4 and just stay there.
Is that defining lambda to be a vector, taking on values in the range from little bigger than 0?
There is work in that. There are other ways to keep lambda scalar and get a better value than either 1, half, 2. So you get intermediate values by optimizing. You can get a vector value of this, and each one go in a certain way. Each of those other procedures ends up taking more computer time, and the whole trick here is getting the right trade-off. Because the reason you're doing this is you want to change the scalar rather than recalculate the Hessian. Unfortunately, to get the optimal vector of lambda, you need to know the Hessian. And if you're going to calculate the Hessian, you're already in a new iteration. So the idea is these are like tricks that make things faster. So now, Gauss actually uses a procedure that chooses the optimal size of this but keeps it a scalar. It's a good point. Okay, the third point here is, will we always get an increase? The way I've drawn it, we would always get an increase, but we need not. And that's because the function might be not concave at the point that we're looking at, and Newton-Raphson will send us in the wrong direction. I'll get rid of all this. except part here. Okay. What if you've got a function looks like this, and you're here? There, the curvature is positive. The slope's getting positive. You take the negative, the inverse of a positive is a positive. Take the negative of that, and then you're going in the opposite direction of the slope. So in this situation here, NewtonRaphson would send you whirling out in the wrong direction. So NewtonRaphson has the possibility, if you're in a convex portion of the likelihood function, to move you in the wrong direction. If the function is globally concave, that is, there are no convex portions, then it will always move you towards an increase. But most functions that we're going to look at when you get into simulation, you end up with complicated functions that will have convex areas, and NewtonRaphson will push you in the wrong direction. So if you're applying NewtonRaphson and you get an error message back from your routine saying failed to find increase, what it would do is it would go out, do its procedure, find that you don't have an increase with a scalar of 1, then it'd try half, then it'd try a quarter, then it'd try an eighth. Somewhere in the code it says if it's below a certain value, give up. You know, if it's below 1 over 2 to the 10th or something like that, then just give up. And when it's reached that point, it'll send out a message saying NewtonRaphson failed. That could be because you're in a convex portion. And that gives rise to other procedures. Okay. The other way that you could get that message, though, and this is important, is that you could be in a situation like this, where there is an increase. Quadratic gives an move all the way to there, but the function actually is highly non-quadratic, so you're going in the right direction, but every time you have it, you have to have it so much to get an increase that you've hit your criterion of saying, you know, we've tried hard enough, we're not going to find an increase. Your computer has to have a stopping rule, so when you have this scalar over and over and over, eventually it has to stop. You can hit that even though the slope is positive and you're in a concave portion of the function. And yet what's happening is that in the direction you're moving, the maximum is so close to where you are that it can't find any increase. That doesn't mean you're at an increase. It could mean that you've got in 3 dimensions, you've got a maximum way up here, but not in this direction. Okay, so you just, you know. So those are the 2 ways your NewtonRaphson can fail. It can fail to find an increase because you're in a convex portion or because you're in a concave portion, but it's so highly non-quadratic it can't find an increase.
Is it computationally taxing to figure out whether the Hessian is negative semi-definite?
It's not that hard. Calculating the Hessian is extremely difficult. It's time consuming. Taking the inverse, you find out immediately whether it's you know, not positive definite if the inverse doesn't exist. No.
But in that event, can you not?
Actually, no. I take that back. How does it find that? I can't think of that right now. So let me move on. But in any case, this is the motivation actually for the other procedures. It's really rare that you would actually use NewtonRaphson. It provides an extremely good way to think about the maximization process, but it doesn't, from a practical perspective, work well for 2 reasons. I've already mentioned. 1, you require the Hessian. The Hessian is extremely hard for a computer to calculate. It essentially has to take k squared divided by 2, or about that, evaluations of the likelihood function. And secondly, it doesn't guarantee an increase. So what that then leads to is a variety of other procedures which, instead of using the inverse of the negative of the Hessian here, use something else. Yeah?
Well, when I get this error message on the Newton-Raphson method, couldn't I just start like another beginning?
Yeah, you can. You can start at another place. And that's often what you'll do on all these procedures. You'll just say, well, I know it's got a maximum somewhere. I'm going to try somewhere else. Yeah. Okay, the second procedure then is VHHH. This is after Berndt, Hall, and Hausmann. And the second or first Hall was Bronwyn Hall, who teaches here. To do this one, we need some new notation. And this is where keeping your notation in mind is extremely important. This is our formula. So now let's define a gradient matrix. And before doing that, let's define the log likelihood vector. Okay. This is the log likelihood function, which gives you a scalar as an output. Okay. What we have here is I define it as LL, little l's. It's a function of beta. It is the vector of log likelihoods for each individual person, for n people in your sample. Okay. So the log likelihood with capital L's is the column sum of this. Okay. So this is a vector of size n by 1. Usually when you actually program up your thing, you're going to have the output of your log likelihood program give you this vector, because you'll use this for a variety of things, and then sum it up to get the value of the likelihood function. So usually you actually produce this as the output of your proc. The gradient matrix then is the derivative of this with respect to each of the parameters. So the gradient matrix I call capital G. It's the derivative of the log likelihood vector, which is a column vector with respect to beta transposed as a row vector. So this is, this is n by k. It is the derivative of the first person's log of their probability with respect to the parameters on up to the last person. Okay, so this is n derivatives. Each one is with respect to a row vector, so you get k rows, columns. Okay. And this is the column sum of that. Okay, so this is n by k. You add up all the n's going down, you get a 1 by k, and that's transposed as that. Okay, what the VHHH procedure does is to calculate a matrix B, which is G. Okay, this is called the outer product of the gradient. This is very important. When you're giving talks or something like that, people are very sloppy about their terminology. Often people refer to the gradient without differentiating the gradient vector from the gradient matrix. So when you're saying outer product of the gradient, well, it could be different form depending on which of those two gradient concepts you're thinking about. Whenever it's used, though, it's nearly always in reference to the gradient matrix. It's the outer product. So this becomes now, since it's the transpose, k by n. This one's n by k. So the whole thing's k by k. What you're doing is taking the squared, you're essentially taking the squared elements of the gradient matrix. For each person, you square their gradient and sum it up over people. Okay. So this is, if you're at where the mean vector, the gradient vector is 0 at the top of the hill, this is simply the variance of the gradient over people, because you subtract out 0. Otherwise, it's outer product. Okay, the VHHH procedure is to use this as this matrix there. So essentially, you replace the negative of the Hessian with this outer product of the gradient.
Information and everything? The idea behind it was the information.
That's right. Okay, how many of you remember from your Econ 240A or B? By the information identity, this outer product of the gradient approaches the negative of the Hessian when, what 3 conditions have to apply? 1, n has to approach infinity. So as you get a larger and larger sample, the outer product of the gradient approaches the Hessian, negative of the Hessian. What's the next one? Each of these is important because each of them will determine whether the information identity is valuable for you or usable. And you'll see there's a lot of simulation situations where we can't use the information identity. You got to know when you can and when you can't. N has to be large enough for the asymptotics to work. Secondly, you have to have a correctly specified model. When you don't have a correctly specified model, this does not hold, and something else does, in fact, that we'll see. So you want to know, often simulation can be seen as a misspecification. You're using, instead of the true integral, you're using some approximation. So it's technically misspecified, and your information identity doesn't hold exactly. What's the third thing? At the true parameters. It doesn't hold everywhere. It only holds at the true parameters. Okay? So as you're reaching the maximum of the likelihood function, the outer product of the gradient will become a better and better approximation to the negative of the Hessian, because the top is probably going to be more like the true parameters than anywhere else on the function. Okay. So you need to know that this approximation works well and works essentially like NewtonRaphson when the number of observations goes up, correctly specified model, and you're near the true ones. Of course, you can use it even when you don't think of it as an approximation to the Hessian. All it is some k by k matrix that you stick in here. Okay? And under those conditions, we'd want to think of, why would we want to do that? Why do we want to use VHHH instead of NewtonRaphson? One reason is you don't have to calculate the Hessian. The Hessian is extremely difficult, time-consuming for a computer to calculate. Here, all you're calculating is the first derivatives for each person, which you have to do to get the gradient vector anyway. That's the column sum of it. Okay? So if you're going to have to calculate the gradient anyway, you're not taking any extra calculations. All you do is take the outer product of this gradient to get what it's multiplied by.
In practice, do you have to divide the outer product by n?
It cancels out if you do averaging or not, because of it enters here also. That's number one. Number two, the second reason you want to do it is that it guarantees you an increase. Okay? This function b is always positive definite, and so you will always have an increase, even in a convex portion of the likelihood function. So you will always move in the direction of the gradient. Essentially all it's saying is that this function is a generalized positive. It will always move you in the direction of the gradient. So you'll always be moving uphill. Now, you might only be moving uphill for a point very close. You might have a situation where the gradient is positive, so you're moving uphill, but you're not going to go very far. And so this procedure can fail if you take a VHHH step with the scalar equal to 1, have it, and keep having it, until you get to where whatever your drop-off point is, and you still haven't reached an increase. That could be because you only have an increase in a very small neighborhood. So at least that eliminates one of the problems of one of these failures with NewtonRaphson, which is if it's convex, you're going in the wrong direction with NewtonRaphson. With this one, at least you're going in the right direction. But you can still have the problem of an increase being only in a very small neighborhood around your original value. Essentially, it's telling you that the gradient is not moving you in the direction towards the maximum very much. It just happens to be the gradient at that point, whereas the overall maximum is somewhere unrelated to that. Yeah?
How big of a problem is this? I mean, after all, that means that you're very close to the maximum.
No, it does not mean that. And that's what's essentially important. You could have, in a three-dimensional thing, you could have this going here, but the maximum be way out here, in fact, over here. You know, so it's not even that you're maximized with respect to this dimension. That's the problem. And with these highly non-quadratic functions, you get this all the time. Probit models is very susceptible to it. Logit models with log normally distributed coefficients is very susceptible to this. This is a really big issue, numerical maximization. That's why a procedure we're going to talk about late in this semester, based on Bayesian concepts, actually gets away from all these problems. You never maximize a function. You take draws from a distribution, and the average of that is equivalent to maximum likelihood, we'll show. So you never have to maximize anything. It's really neat. But nevertheless, if you're staying in these maximization procedures, which 95% of the time you will, you have to realize that just because you fail doesn't mean you're near the maximum. Yeah.
Follow up on this. So what that means is that basically in the gradient, one of the elements in the vector is 0, right? There's one with respect to 1 beta, right? So this slope is 0, well, or close to 0. So we can't be moving because we're on a sort of a hump here. Could we somehow turn it around and make it?
Turn it around and?
Well, I guess that means that you can basically start a different starting point, right? That's what it would.
Yeah, that would be starting elsewhere. Usually, if you know how to correct a problem, how to put this? If you knew your likelihood function well enough to know how to correct these problems, you wouldn't need to use these general purpose maximizers. You'd try to use the structure of your model to start with. And so when you have this, generally you won't know what the problem is. But yeah. Okay, another approach, just to kind of get the whole set that you might be dealing with in our workshop, is, let's leave this here. Steepest ascent. Here, you just go lambda, the scalar, times the gradient. So you just go in the direction of the gradient. Essentially, m is equal to the identity matrix. What you can do is prove that this maximizes. This gives you the highest possible increase in the likelihood function for a given distance of a step, or a step size. So you maximize the Lagrangian, which is a first order Taylor's expansion of this. Subject to, in fact, if you put a negative here, it works nicer. Subject to the constraint that the distance is equal to some k. This is the squared distance. Okay. So what you're doing is a constrained maximization. Maximize your expression for the likelihood at your new value, subject to moving only a certain distance. And you'll find that the maximizing value gives you this formula. It's interesting, though, I have very seldom found this to be a useful technique. You think it sounds good because for a given distance, a given radius around where you are, this gives you the maximum increase. You'd think it'd work, but somehow it just takes lots and lots of steps. Yeah?
I was just asking, what's the first thing? I understand what's written there, but what is the first thing?
First order Taylor's expansion. You want, okay, so this will be
Of that expression.
of this expression here, the log likelihood. The log likelihood at the new value, because you're trying to maximize the log likelihood. It's the original value, and it's a first order, so it's just the difference. That.
I thought it was an extension of the above.
Right.
It makes sense.
Okay, now there's two other procedures that are actually quite good, but don't have much intuition. I think the reason you understand these procedures is, one, just so you can program or put them in or use them, but more importantly, it's to understand what's going on, what's the structure of maximization, what's the structure of your model. These two procedures don't really give you much intuition, so I'm just going to describe them briefly. The first one is Davidon-Fletcher-Powell. DFP, Davidon-Fletcher-Powell. And the other one is Broyden, Fletcher, Goldfarb, and Shano. No one ever remembers those names. BFGS is what it's called. This one is actually quite effective. And I use that as my default when it's written up into code. Gauss has that as the default. You can choose other ones. But what each of them do, recall that NewtonRaphson puts in the Hessian here. BHHH puts in the outer product of the gradient, which is a kind of measure of the Hessian under the information identity. What these do is to get an approximation to the Hessian by looking at how the function has changed in the iteration process. As you move from one point to another point, it can calculate how the gradient, it has to calculate the gradient anyway, so it calculates how the gradient has changed between those 2 points. And then you get a third point, it uses information on how the gradient has changed from each of those 3, and uses that to construct an approximate Hessian. Instead of being the Hessian that's appropriate at one point based only on information at that point, it uses the structure of the movements from one step to another to calculate something that looks like a Hessian that gives the right curvature as implied by those points. So as you take more iterations, you get more and more information on what the Hessian for this function must be. You no longer have to rely on the idea that it's all quadratic, because you're using information throughout the whole range. Now, what's problematic about each of these approaches is
it takes a linear average, or?
It's kind of like a linear average, but the idea is, suppose a quadratic would look like that, and you move from here to here, and your function's there. It will tell you that the curvature is smaller than what you'd expect only looking at the curvature here, because it takes this derivative and that derivative, the change of those two derivatives divided by the distance between them is a measure of what the second derivative is. So it uses that discrete information. That's good because it doesn't rely on these ideas of information only at one point. It uses information as you flow through. What's problematic then with these is if the curvature of your function changes as you move along the iterations. And in fact, this one uses recent information more than past information. That's one reason it's good. But both of them kind of approximate that. Did you have? No? Okay. Couple of things here, and then I want to talk about our computer codes. First of all, convergence criterion. We've talked about how to move up this likelihood function. How do we know when we've moved far enough? Well, we know theoretically we're at the maximum when the gradient's 0. And I don't want to maximize that. The maximum occurs where the gradient vector is 0. Each element is equal to 0. Numerically, that you never get zeros. You just can't get a 0 out of a computer. It just doesn't happen. You get something that's real close to 0, perhaps. And in any case, what you can be is so close that you really don't care that you're close enough. You don't want to spend the extra time it takes to move to where the gradient's exactly 0. You don't trust your estimates that much anyway. So you don't really use gradient equal to 0 as your criterion. So then the question becomes, what do you use as the criterion? What is a reasonable concept to determine whether you're close enough to the maximum? The criterion that I like, and that I think most econometricians like best, is to use G H inverse G. So this is there. So this is k by 1, which becomes 1 by k. It's k by k. And this is k by 1. So the whole thing becomes 1 by 1. This is valuable because it's the test statistic that you would use to test the hypothesis that the gradient vector is 0. So it has a hypothesis testing concept. It's distributed chi-squared with degrees of freedom equal to the number of parameters that you've got. Okay? So if you were testing whether your hypothesis of the gradient being equal to 0 were true, you would use this test statistic and do it against a chi-squared. That's kind of the motivation for it. However, you will probably want to use a much stricter, smaller value of this to determine convergence than simply that you cannot reject the hypothesis of convergence. Usually, this will be the region in which you cannot reject the hypothesis of the gradient 0 is pretty wide. You know, it might go somewhere around like that. It's kind of like, you know, oftentimes your point estimates will get t-statistics of 2, which means your 95% confidence interval, you can't reject anything between 0 and twice as high. That's a pretty wide range, and you'd like a little more precision than that when you're getting to the top. So usually this is set extremely low, much lower than you would have for a test statistic. In fact, 0.001 is what I've got in my program. You can change that. But you know, a chi-squared with just 1 degree of freedom is 3.8. So obviously you're much lower than the test statistic. So this is one convergence criterion. Convergence criteria that should not be used are, suppose you're iterating and your parameter values don't change much from one iteration to the next. Some people think that means you must be close to the maximum. You know, you're kind of getting here where things aren't changing much. That's wrong. What it means is that you could just be at a point where a quadratic gives you a very small step because you've got a very high curvature at that point, but you're nowhere near the maximum. Okay? It also could mean, well, that your function is highly non-quadratic, and so even if the quadratic would take you a long ways, you keep having your step size, the lambda, and you end up with a very small change. So all that's telling you is you're not doing too well in iterating. It's not telling you you've reached the maximum. Similarly, if you look at the likelihood function itself and say each iteration things aren't changing, you might think, well, that means I'm up here where things aren't changing much. But again, it could mean you're just not iterating very well. You're not moving towards the maximum very fast. So those are not good criteria to use. One criteria to use that is often applied is that the gradient is less than or equal to some value k, which you set at whatever level you want. This is now a element by element comparison. So it's a dot less than. Each element of this is less than this scalar. This is a fine criterion, and it's obviously related to what we're wanting things to be real small. The problem with it is that you get into scale issues, that parameters that are scale large, what k you would want to use will depend on the scale of the variables that you enter, which determines the scale of the parameters. For example, if you have cost in there, you put cost in dollars, you're going to get a smaller coefficient than if you put cost in thousands of dollars. And so you would need to keep adjusting your convergence criterion to account for that. To do that, this is an element by element division. You can say that the relative gradient is less than some amount. And this is what's used by Gauss in their program. Okay, let's take a break. where those are your maximum likelihood estimates. You're maximizing the likelihood function. Now you want to know what are your standard errors for these. You remember, hopefully, from your Econ 240A and B class that the true parameters minus your estimated parameters normalized by the square root of n approaches in distribution a normal with zero mean. So that means your estimated values, as your sample size increases, become distributed around the true value, so they're consistent, and have the Hessian inverse as the covariance matrix. So your covariance of your parameters is equal to 1 over n h negative 1. Again, I like to keep the negative along with the Hessian because that allows you to compare with other things. So this is your covariance matrix. If you want to get this, then you have to calculate the Hessian at the last step, even if you didn't do it along the way. Okay. However, you can also use the information identity for a correctly specified model and use B instead. So your covariance matrix becomes that, or getting rid of the parentheses. So this is using the outer product of the gradient. So if you're using the VHHH procedure along the way, you might as well use it at the last step also as your approximation to the Hessian for getting your standard errors. This is for a correctly specified model. Correctly specified. If your model you think is not correctly specified, but you think your first order conditions still apply, so your estimates still are meaningful for you, then you use the results from a generalized method of moments procedure, which tells you that this is now Hessian inverse, outer product of the gradient, Hessian inverse. Is that right? Or is it the other way around? That's right. Okay. So the covariance then, in this case, is 1 over n Hessian inverse. This is now B, your B triple H matrix, outer product of the gradient. That. Here you have to calculate the Hessian at your last step to calculate the covariances because the information identity doesn't apply since you've got a misspecified model. We will see that simulation can be seen as a form of misspecification. And so this is the correct covariance matrix to use when you're using simulation. Your parameters are still consistent because as the number of draws goes up in your simulation with the sample size, you still have zero mean to this distribution, but it's got a different covariance. As the model becomes better and better, your simulation becomes better and better, this will approach that because the misspecification will go away and you get the canceling out. B will cancel with H negative, and you just get it. Okay. Okay, so now, our problem set. Pass these out. Pass those back. Whoops, don't smash your glasses. Here's some. This problem set, you're going to first estimate logit models.
I'm sorry. When you use B, goes to negative 8.
Over to the right.
Yeah, here.
Goes to negative.
B
B
goes to
approaches to the left.
To the left.
B approaches negative.
not inverse.
Not inverse.
Thank you. Okay. In the problem set, you're now going to estimate logit models where you actually have a a procedure that calculates the likelihood function and a procedure that maximizes it. So this isn't going to be transparent to you as it was in SST. You're actually going to do it. The purpose of this, obviously, is not to estimate logit models in this laborious procedure. It's rather to learn the way in which you write your own likelihood functions and maximize them, so that if you ever want to run your own kind of model that's not in existing software, you'll know how to do it. The problem set is going to have 3 computer codes that you will use and then modify. And I want to go through these to explain what's going on so you can understand the code. I've handed them out. They're listed as job 1, 2, and 3. Okay, but before we get into that, I forgot I should tell you how to get into Gauss. Okay, so if you're running a Gauss job, all from this point on in this class, you will be running Gauss. In your Unix prompt, what you need to do is say Gauss.lab. This is the version of Gauss, not the version, but the license that we have for this account, for this class. We have 30 licenses, so 30 people can use it simultaneously. If you left off the lab and just did Gauss, that's what the department has as their license. There are only 6 licenses available. So you probably won't get on, and if you're getting on, you're going to prevent someone else from getting on. So always put the .lab. There's plenty of them. There's 30. We've got 39 students, so it'll work. Negative B, the file name. So this is your command file. And then that, so that it runs in the background. Okay. There's other ways you can do this if you prefer. If you want to pull up the Gauss window, you can do Gauss lab ampersand, and then a window will come up with a Gauss prompt. So you're now in Gauss interactively. You can do whatever you want to interactively there, but my idea is you'd set up your command file and then just say run and then the file name. Okay. That way you always are editing your file and making sure it's got everything you want, all your lines and everything correctly, and then you just run it. It'll give you error messages if you made mistakes or whatever. So you can do it either way. This will print to whatever output you've specified in your command file. You can then pull that up and look at it. This will print to the screen as well as to your output file. Yeah?
Command file or the output file?
This is the name of the command file. The command file will have in it a Gauss command that identifies the output file. Okay, so here is the first job that you'll run. I did it here in bigger print, so hopefully you can see it. This is say start a new job, get rid of everything that's hanging around from your old jobs. It's really useful to start that way, because then if you've got variables defined that you forgot about, this gives space to hold the program. That says turn the screen on so you can see the output. This tells you what the output is. So you change this part here to whatever your output name is going to be. In this job, I've set the number of observations as 900 and the number of alternatives as 5. These are the data that you've used already. 900 houses, 5 alternatives, and then I load in the data. These are exactly the data you used before, but in ASCII file instead of SST formatted. So we're reading in a matrix, which is 900 rows, 19 columns. And those 19 columns, each of them is the variable, one of the variables that is in the data set that you've already used. So it's installation cost for 5, operating cost for 5, that's 10 altogether, and then the demographics. What this does is read in the dependent variable, which identifies, dep ID is a variable that I created that identifies the chosen alternative. So it's 1, 2, 3, 4, or 5. What works well with the code that I've written for doing maximum likely, for doing the logit model, is to have, instead of a number, to have a matrix which is number of observations by number of alternatives, and it consists of zeros and ones. So if the first person chose the second alternative, it would be a 0, 1, 0, 0. The second person chose the first alternative, they'd have a 1, 0, 0, 0. So what this part here does is to create a new variable called dep_m matrix, which identifies with ones the chosen alternatives and zeros otherwise. This is very useful because you can multiply this matrix times your matrix of representative utilities, and all of them will be zeroed out except the chosen one. Then you read in installation cost. It's columns 3 through 7. That's 5 columns. Operating cost, 5 columns again. And I divide it by 100 just to get the scale right, or easier. Notice that these are number of observations long, because 900 by 5. Okay, 4. I'm sorry. Is it 5 or 4? 5 alternatives. Okay. So each of these is number of observations by number of alternatives. Okay. And what I'm going to do then is to reshape them. There's a Gauss reshape command which says take this matrix and change its shape to where it has this many rows and that many columns. So what I'm doing is transforming that into something that is number of observations times number of alternatives times 1. It's a vector now.
Like a vec? The vec command?
I think the vec command would do this also. But it's easier to think of it this way. I like these because you can then easily scan and make sure you know what the dimensions of your variables are. So what this has done is now put 5 rows for every person. And there's one for installation cost, one for operating cost, etc. And then I can concatenate them. So this is the installation cost vector, operating cost vector. Each of them has 5 rows for each person. Concatenate them together, and now we've got a variable, a matrix, that is number of observations times number of alternatives. So you get 5 rows for each person times the number of variables. In this case, 2. But if you wanted to have more variables, you just concatenate them on and just extend it this direction. So that way you can hold all your data in one matrix instead of having can't have 3-dimensional matrices in Gauss.
And you don't have to specify anything to reshape to do the ordering in the way you want?
Well, what it does is reshape with this how many rows and that many columns, and we'll take them in the order that they're currently and put them in the new order, always going across a row before it goes to the next column. Okay. It picks up across a row and puts across a row before it goes to the next column. Next row. Yeah.
That's a little hard to understand. What does this create resultant matrix? What will be an entry of it?
This will be installation cost and operating cost as the 2 columns. And this is installation cost for the first person for the first alternative, installation cost for the first person, the second alternative, installation cost for the first person, the third alternative, up to 5, and then you go to the second person. So you've got 5 rows for each person. Okay. So here we're holding 5 rows of data for each person for the 5 alternatives. You've got 3 dimensions going on here. You've got number of variables, number of people, and number of alternatives. If you could hold things in 3-dimensional arrays, it would really be great. But Gauss doesn't do that, and most programs don't. Okay, then all of this is just putting the data in a way that's going to be compatible with how I've written the likelihood function. Then on this program, I'm using the Gauss maximum likelihood routine. So it'll do all this iteration to the maximum for you. You don't have to write the code to do it. You start with starting values. B is equal to the starting values. You have to have one element here for every parameter in your model. If you revise the model so it's got different parameters or whatever, you've got to always make sure you've got as many elements of this starting value vector as there are elements, parameters in your model. Okay? These aren't necessarily coefficients. We'll find they can be covariance terms, whatever, later. XMAT is a peculiar thing that maximum likelihood routine in Gauss wants. It wants a variable to put as its first argument. The only thing that variable is used for is to tell maximum likelihood how many observations there are. It counts the number of rows of this matrix and says that's the number of observations. It's a really weird way. I think it was originally started when all you would do is read one data matrix into your likelihood function and be done with it. But usually we read lots of data matrices in, you know, dependent variable, all these various things. And so all that this does functionally is tell how many observations there are. So what I always do is just say xmat equal ones. That's a matrix of ones that has that many rows, that many columns. So it just has ones for a vector of length number of observations. And that then is used by Maxlike to determine how many observations there are. It's just a peculiarity of their program. Library means pull in this program. This is part of that library routine. Here, these variables that start with an underscore, those are variables that are defined by Maxlike itself. You can't, if you tried to define a variable named this, it would give you an error message. What they do is give parameters to the maximum likelihood. These are the three that I'm just identifying here. There's, I think, about 10 altogether. This is the maximum tolerance. That's the convergence criterion. Okay. This is how many iterations you have. If it hits 50 iterations and hasn't found a maximum yet, it quits. So this is good, so you don't want your program just running and running when you know you're at a point where nothing's happening. And this tells it which algorithm. 5 is BHHH, 2 is BFGS. I say in the README file what each of them is, or in the exercises. Okay. So you change the algorithm by changing that number. And then it does maximum likelihood, bringing in XMAT, which tells it the number of observations. This 0, which I don't remember anymore what it means, it's just another, I always use 0. And then you give it the name of the likelihood proc. You can look these things up, it's all online help. This is the likelihood proc. This is the procedure, which is defined down here as a separate procedure that calculates the log likelihood function. So you can, whatever name you give this, you stick it here. I've got LL because that makes sense. You could have it like my LL and put it in if you redefine this. And this is the starting values, the vector of starting values. So the first two of these are irrelevant. You just stick them in like that. This gives the number of observations. I don't know what that does. That is the name of the likelihood function. That's the starting value.
What's the number include Maxlike.x?
This is include a particular part of Maxlike. I set this up like 5 years ago and don't even remember what these are for. You know, you read the manual once, you find out how you're supposed to do it, and then you just do it. So you can reread and figure out if you want other options. Here's the log likelihood routine. What's interesting here is this is what it takes to calculate the log likelihood of a logit function. Jeff Dubin charges, what, $600 for his program? It's got like 5 lines of code. It's amazingly simple. And you can, you know, when you write your own likelihood functions, you'll find that just because a certain model doesn't exist in pre-existing software doesn't mean it's difficult. You know, sometimes you'll just take one extra line of code to make what you want. Okay, what this does is I put a note here saying that I'm using globals, that is variables that I've already defined earlier in the program. Then I'm also going to create 2 variables that only exist within this procedure. This is like a subroutine.
What are the arguments B and X?
B is the starting values. That's important. If you're creating a likelihood procedure to be read by Maxlike, it has to take 2 arguments. The first one is the starting values, and the second one is a data matrix. It will put XMAT into that. And so again, I don't ever use X anywhere in here. It just tells the procedure. It's kind of like a holder, a dummy holder. But if you wanted to loop this and use different data each time you looped it, that's when it would become relevant. So your log likelihood proc has to have 2 elements reading in, the starting values, and then this placeholder, essentially, which I'm calling XMAT. It'll read it in here. Then I create exponentiated representative utility, the V, and probabilities. So first thing is I take the variables. Notice that they are n-var wide, and I multiply them by the coefficients b, which is n-var times 1. Okay. So this is matrix manipulation, matrix multiplication. So what it does is take installation cost and operating cost and multiply them by these two. It goes across the row and down the column and it ends up producing something that is 1 by number of observations times number of alternatives, which is the exponentiated representative utility of each alternative for each person. So now I've got something which, because I've got the variables multiplied by their coefficients for each person, and then I exponentiate that, stick it in here. The second one is for the second row, and that's, so you get 5 elements for each person, which are the exponentiated representative utility for those 5 alternatives for the first person and the second person. I've got all my exponentiated representative utilities there. Then I reshape it.
When you define B, you define like curly bracket. Is that the way to say?
This is create a vector.
A vector.
Actually, a matrix. Vectors and matrices are not. A vector is a matrix with only one column here. So a curly bracket means it's a matrix. You're defining a matrix. You put the numbers. Each row is without commas. When you put a comma, that says start a new row.
So spaces would be.
Spaces are columns within a row.
Okay.
Right. So what you want here is a column vector of B. Okay. So now I've got something that's number of observations times number of alternatives long, 5 lines for each person, times 1. Okay. And then I reshape it to where now I have number of observations times number of alternatives. And E beta x11, E beta x12 for the first person, first alternative, first person, second alternative. 5 alternatives. So the reshape command says reshape this matrix, which used to be number of observations times number of alternatives long and 1 wide, to be number of observations long and number of alternatives wide. Okay. Then I multiply this by dep m. And remember that dep m was number of observations times number of alts. Okay, with zeros for the non-chosen alternative and 1 for the chosen. But now, instead of using matrix multiplication, I use element by element multiplication. So each element in this matrix is multiplied by the corresponding element here. So this multiplied by 0 gives you a 0. That multiplied by that gives you this. So essentially what that does is save only the chosen, the exponentiated beta x for the chosen alternative. Okay. And then, so that's what this here does. Sum C takes column sums. So what I've now got is something that is number of alternatives wide, number of observations long. I transpose it so that it is like this, number of observations, number of alternatives, okay, and then take the sum. The sum of zeros and the exponentiated value of the chosen alternative is simply that collects the chosen alternative's exponentiated representative utility. And then the denominator, I sum over all of them. I don't just sum over the ones that are held as the chosen, but I sum over all of them. So it's this matrix, these 5 summed together give me the denominator. Okay? And then divide the two to get the probabilities. And then return to the main program, Maxlike, the log of those probabilities. So the outcome of this is a vector which is number of observations long by 1 of the log of the probability. Okay. So it's 1, 2, 3, 3 lines of actual manipulations and a return for logit. Extremely simple. So now what you will want to do is go in here and change things. For example, what if you want a different scale for some people than for other people? How do you do that? Other things. Okay, so that's job number 1. Any questions on that? When you get into this, you know, a lot of this sounds like it's a lot to take in all at once, but when you actually start working with it, it becomes easy. Then, job number 2, all we're doing in job number 2 is specifying, in addition to the log likelihood function, so the first page is essentially the same. When you get to the log likelihood function, right above it, it says grad proc equals this. We're now specifying a gradient procedure. The way we did it in job 1, the gradient is calculated by the maximum likelihood routine explicitly in a numerical fashion. It calculates the likelihood function to start, and then it'll change one of the parameters by a tiny amount, recalculate the likelihood function, and take the difference in likelihood function divided by the change in the parameter as a numerical estimate of the gradient. So it essentially is explicitly taking gradients numerically. That's time consuming. That means it has to evaluate the likelihood function once plus once for every parameter. Okay? And take those differences. Instead, we can supply it with a gradient function that'll calculate the gradient for it analytically. Usually this is faster. If you're going to do that, you tell the procedure, the Maxlike, I want to provide a gradient proc, and you write it. Okay? This is important to know in both ways. A lot of times you want to run a model, you don't care about runtime. You're going to just let it go overnight. But you do care about spending your own time writing code. In that case, you leave off the gradient proc, just do the likelihood thing and let it chunk away. But if you're going to use it over and over and over again, and you do care about time, computer time, then you invest the time to get the gradient proc in there and add it, you know, and then each time you run it, it's quicker. So it's kind of a decision you need to make of where you want to spend your time, having the computer chunk or having you write code. So this is the gradient. What this uses is the fact that the gradient proc for a logit model, change in the log of the probability for person n with respect to beta, is equal to the sum over all alternatives of a dummy, which is 0, 1 for the chosen alternative, minus the probability times the vector of explanatory variables for that person. So this is k by 1. Okay. These are scalars. Notice that this has an analog to regression. This is the residuals. Residuals times the explanatory variable. We want the gradient to be equal to 0. So what we're doing in maximum likelihood on logit is essentially what you do in regression. You set the residuals times the explanatory variables equal to 0. Find the parameters that do that. So the second job, all we've done is add this gradient proc. And just show you how to do that. The third job then, sometimes you will want to control the maximization in a way that you can't do with Maxlike. Maxlike does its things in a particular way. You can choose the algorithm, you can choose a lot of things, but you can't control it. For example, it uses a criterion for convergence that's different than what we'd like to use. It uses the relative gradient rather than the gradient times the inverse of the Hessian times the gradient. And so what you might like to do is have your own maximization routine. And this is one. This does VHHH. You can revise it to do other things if you want. You should run through this and see what it does. Notice that most of this is printing. It's harder to print in these programs than anything else to get nice looking output. But all it's doing here is taking the gradient. This is the gradient matrix. Taking the inverse of the outer product of the gradient to get what you're calling the Hessian. Taking the sum, column sum of the gradient to get the gradient vector. This is the convergence criterion. The gradient vector times the Hessian times the gradient. This is the Hessian inverse. And then if you meet the criterion, you stop and print out all this junk. If you don't meet the criterion, then you take a step. And the step size is the inverse of what we're calling the Hessian times the gradient. We start with a scalar of 1. And this loop just halves that scalar if you don't get an improvement each time. Okay? When you finally get convergence from the convergence criterion, then you stop. If you don't stop, then it says failure to find increase, or that you've got too many iterations and it's time to stop, and you're done. The likelihood routine and the gradient routine are exactly like they were for Maxlike. All we've done now is replace Maxlike with our own maximization routine. The Maxlike routine and gradient only have one input because that dummy placeholder that Maxlike uses, we don't need it. Okay, so the idea is you'll be running these, particularly the first one, and revising them as necessary to do other slight changes and kind of just get in the habit of doing this kind of maximum likelihood procedures. We'll use it over and over and over. Okay? Issues, questions? I seem to run over 2 minutes every time so far. Thank you.